Bismillahirrahmanirrahim. So students, in this video we will be solving magnitude is 10 kilonewton per meter. Span of the beam is 10 meters. The support is A, this is B. We have a hinge support here and a roller support at point B. First step of solving this beam is to calculate the reactions. So for that we will apply conditions of equilibrium. Let's apply the first one, which is sigma Fy equal to 0. Our convention is that upward forces will be taken as positive. So Ra is acting in upward direction. Similarly, Rb is acting in upward direction. And the resultant of the UDL is 10 into 10. 10 kilonewton per meter is the magnitude intensity of the UDL, and 10 meter is the span of UDL. So area, the resultant of the UDL is equal to the area of this rectangle. Okay, and let's put it equal to 0. Okay, let me just check the sound. Okay, the mic is on. Let me use my hand free thing. Otherwise there will be some echo. All right, so if we rearrange this equation, let's see, what do we get? We'll get Ra plus Rb equal to 100. And in this equation, we have two unknowns, so we cannot solve this equation. So let's apply the other equation of equilibrium. Sigma mb equal to 0, let's say. And our convention is clockwise is taken as positive. Now, if we take sum of moment about point Ra into 10, as it is clockwise, so we'll take it as positive. And then this resultant will produce movement in counterclockwise direction, so you will take it as negative. How much is the magnitude of the resultant? It is 10 into 10 is the magnitude. And how much is the lever arm of this resultant with respect to point B? It is 5 meters, right? So into 5. Is there any other movement? I think no. So let's put it equal to 0. And in this equation, we have only one unknown. If we solve the equation for that unknown, we will get Ra equal to 50 kilonewton. And this is positive, so which means that our assumed direction of Ra is true. Now let's put that Ra value in equation number 1, and from that we will get the value of Rb equal to 50 kilonewton. If we put Ra in equation number 1, we will get Rb equal to 50 kilonewton. Now again, if you look at this beam, the system is symmetric. So total magnitude of load is 10 by 10 into 10 into 10 equal to 100 kilonewton. So 50 kilonewton load comes on this end and 50 kilonewton load goes on the other end. So this Ra and Rb are logical, makes sense. Now next step is to divide the beam into portions. Let's see what portions do we have in this beam. Now in this beam, if we start from end A and we start moving towards B direction, there is no variation in the loading. We have UDL starting from point A and the UDL is ending at point B, which means that there is no abrupt change in the loading condition at any point. This resultant is like resultant of this entire load. Okay, so this is the resultant uh, of the entire load, and it is acting at this point. But this resultant will be used for the calculations of reactions and movement calculation. But actually, it's a UDL, so we will not say, okay, this resultant is acting here, so we should divide the beam into two parts at this location. No, we will not do that. Okay. All right, so let's move on. So we have only one portion AB here. Now let's consider this portion, draw its free body diagram, and then write down the equation for shear force and bending moment. So portion AB. For portion AB, what is the value of X? X starts from 0 and it goes up to 10 meters, because if we consider a section here, this is X. Okay, so let me draw the free body diagram. We have one reaction here. Magnitude of the reaction is 50 kilonewton. This location is X. And what else do we have here? Shear force V, bending moment M. The resultant of this force will be acting here. If this total distance is X, this distance will be X by 2. And how much will be the magnitude of this? If the intensity, if we denote the intensity with omega, so omega into X will be the portion of the resultant of the portion of UDL that's present on left side of the section. Okay, so this completes the free body diagram. Now let's write down the equations for shear and bending moment. So sigma Fy equal to 0, and our convention is that we'll take upward forces as positive. Okay, so upward force is positive. Now let's write down the equation. This 50 kilonewton force acting in upward direction, so positive 50, minus this resultant which is acting in downward direction. How much is the intensity? Intensity is 10 kilonewton per meter, and this span is X, so 10 into X. What else? This V is acting in downward direction, so minus V is equal to 0. Okay, and if I rearrange this, I will get V is equal to 50 minus 10x. So this is the expression of shear force for this problem. Now, unlike the previous problems where we had just a point load acting on the beam and the shear force was constant, in this problem we have a UDL and the shear force is also varying along the length of the member. How do we know that? We know by looking at the expression of V. In this expression we have X. X is the distance. So it means that as the distance is changing, the shear force is also changing in the member. So we will say at A, X is equal to 0. So shear force will be equal to 50 minus 10 into 0. How much is that? That is 50 kilonewton. And at B, sorry, At B, x is equal to 10 meters. So V will be equal to 50 minus 10 into 10, and that is equal to minus 50 kilonewton. So shear force at A is 50 kilonewton. This is for shear. Now let's move to bending moment. Sigma mx equal to 0. Convention is clockwise positive. Now let's apply sigma mx equal to 0. So about this section, this 50 kilonewton will produce moment in clockwise direction. So we will take it as positive. 50 into x. Then this UDL. UDL, its intensity is omega x or 10x, and the resultant is acting here, so it will produce moment in counterclockwise direction. It will be taken as negative 10x. This 10x is the resultant of the UDL, that part of the UDL which is present on the left side of the section shown in this diagram. And what is the location of the resultant? It is x by 2. So multiplied by x by 2. That is the moment due to this UDL. And finally, we have this m, which is also acting in counterclockwise direction. So minus m is equal to 0. If I rearrange this equation, I get m equal to 50x minus 5x squared. This is the equation of bending moment for portion AP. Now again, we have x involved in this system, so we will have uh, different values of moment at point A and at point B. So at A, x is equal to 0, so m should be equal to 50 into 0 minus 5 into 0 square, and that gives us 0. Now at point A, we have a hinge support, and at hinge support, 0 moment is very logical. At B, x is equal to 10 meters, m is equal to 5 into 10 minus 5 into 10 square. Sorry, this is not 5, this is 50. 50 into 10 minus 5 into 10 square. If we solve this, what do we get? We get 0 again. Is this 0 logical? Yes, this is logical because we have a roller support at point B. So 0 moment at support A and 0 moment at support B. So we have moments and shear forces for the entire length of the beam. Now let's start drawing shear force diagram and bending moment diagram. Okay, we have a simply supported beam subjected to a UDL. UDL, right? Intensity of UDL is 10 kilonewton per meter. Span is 10 meters. Reaction here is 50 kilonewton. 50 kilonewton. These are the guidelines to draw shear force diagram and bending moment diagram. 0 here, 0 here. We are going to draw SFD in terms of kilonewton. Okay, how much is the value of shear at this point that we just calculated? It was 50. How much was the value of shear at point B? This point is A, This point is B. It was again 50 kilonewton. Okay, so we will join this with a straight line. Yeah, it's a straight line, first degree line. This part is positive and this part is negative. So this is SFD. Okay, and what about BMD? 00 line, BMD. Okay, now if we look at the bending moment values that we calculated for this beam, at point A, bending moment is 0. At point B, bending moment is also 0. Now, some people might assume that, okay, at A it is 0, at B it is equal to 0. It means it is 0 for the entire length of the beam. But actually, that is not true in this case. Whenever you draw shear force diagram and bending moment diagram, you need to calculate bending moment at 0 shear location. It's an important point. This is the 0 shear point. The point of 0 shear. If we look at this diagram, 50 and this is 50. So by using the concept of similar triangle, we can see that this point is at mid span, right? 50 here, 50 here. So this is crossing the point at mid length. In some of the cases, when the situation is complicated, we will have to calculate it using some expression. But this time, this is pretty straightforward. 50 on this side, 50 on this side. So this will, if this span total is 10, this will be at 5 meters. So this location, this distance is 5 meters. So if this is equal to 5 meters, we need to calculate bending moment at L equal to X equal to 5 meter. So what was the expression for bending moment? If I write it down here, the expression for bending moment M, it was 50x minus 5x square. Okay, and M is equal to, so at X equal to 5 meters, M is equal to 50 into 5 minus 5 into 5 square. And if we solve that, what do we get? We get 125 kilonewton meter. So the value is 125 kilonewton meter. So you see that at this point, at the point of 0 shear, the value of bending moment is 125 kilonewton meter. So this is 125 kilonewton meter. So we have got this point. Now the next question is that how much or how should I join this point to this point, whether it should be a 0 degree line or first degree line, like a straight line, or second degree, or what. For that, we will have to look at the equation of bending moment. What is the highest degree of X in this expression? It is 2. So it means that from this point to this point and this point to this point will be joined with a second degree line. And now second degree line can be drawn in two ways. For example, if let's say this is 0 point and this is 125. So a second degree line can be drawn this way. We call this as convex up, or a second, this is, let's say, option number 1, and a second degree line can also be drawn this way. This is, let's say, option number 2. So which option should be adopted, option number 1 or option number 2? For that, we will have to go to the shear force diagram, and we will see that what is the variation in the magnitude of shear force. If the magnitude of shear force is decreasing, then the slope of bending moment diagram should also be decreasing in this region. And if the magnitude of shear force is increasing, the slope of shear force diagram should also be increasing. Now, how do we decide that? For that, we need to draw tangent at the curve. Let me draw this. What is the slope of this curve at any given point? For that, we draw a tangent. This is the slope. Let's say this is theta1. And what is the slope at this point? Then if I draw a horizontal line, This is, let's say, theta 2. So the slope of this curve is actually decreasing from this point to this point. So this is a curve with decreasing slope. And what if I draw a curve like this? It's 0 here. This is a tangent. It's exactly horizontal. If I draw a tangent at this point, how much is the slope? This is, let's say, theta 3 in this case. Here, magnitude of shear force is decreasing. So we will draw a curve with decreasing slope, and it will be somewhat like this. The slope of this curve is, it has some value here, and the slope of this curve is 0 at this point if I draw a tangent here. And now in this portion, the magnitude of shear force is increasing. I'm talking about the absolute magnitude. It is increasing in this direction. So the slope of bending moment should be increasing. I repeat that the magnitude of the shear force will be related with the slope of the bending moment diagram. We will prove this relationship in future, but as at this point, we will just consider this relationship as it is. So 0 slope, and then this is increasing slope. Slope of bending moment diagram is 0 here. If I draw a line here, it's 0 here. It's a tangent at, I've drawn tangent at this point, and that tangent is exactly horizontal. So slope is 0, where it has some value at this point. So this is the bending moment diagram. And we have completed the bending moment diagram, and this bending moment diagram is second degree in this portion. Similarly, it is second degree in this portion. This completes the bending moment diagram, and the entire bending moment diagram is positive. And what is our convention? Positive means sagging. So the elastic curve will be something like this. This is the elastic curve. So this completes our problem. We have drawn shear force diagram, bending moment diagram, and elastic curve. So I will stop recording our session at this point.